How well do you know your limit? How well do you know your limit? Hello, everybody. Yesterday, I got a question from Bernard. Bernard sent me three limit questions that we are studying limits this semester, and he gave me these three questions that I should attempt. So I just said let me just put because these questions actually require fun when I was solving them. So I said let me put it out there on YouTube. Okay, the first question was for me to find the limit of 10. Let me use different markers to show different, to show the variables from the numbers. 10 power of t minus 2 power of t minus 5 power of t plus 1 all divided by t times t. Now what I'm going to do, what my goal? As I was solving this, I said let me solve with you as different ways as much as possible. So the first method I'm going to solve using algebra. Then the second of all, I'm going to apply L'Hospital rule. L'Hospital rule is like a cheat code in mathematics. If you have to find, you want to find the limit of u divided by v, and these are indeterminate form, maybe 0 divided by 0, even divided by infinity, or all those other forms, infinite power of infinity, all those kind of things. You can just differentiate numerator with respect to something. Let's say u dx divided by ud. If it is x, the limit as x tends to then to dx. If it is the limit as y tends to then to dy. The limit as c tends to then. So let us call it a. So a tends to something. Then you have a ud a divided by d v da. The days can cancel, so you just have u over d. Good and fine. So we are going to find u dA, and you're also going to differentiate. And basically, just differentiate the numerator and differentiate the denominator. So you can now apply that limit here. And also, in case here too, you are still getting an indeterminate form, maybe 0 over 0, you can still apply the L'Hospital rule again here. You can still apply it as much times as needed till you get a form that you are not going to have divided by 0 over 0, not divided by 0. 1 divided by 0 is not an indeterminate form. It's actually going to infinity. But 0 divided by 0 is an indeterminate form. Even divided by, or infinity minus infinity. Okay, so let's find this limit. I'm going to give you some time. If you want to try it, you can try it out in the next second. 3, 2, 1. Let's go. Okay, the first method I want to use is using algebra. That is only algebra. I'm not going to apply any calculus, just algebra. So first of all, if you are seeing this, you can start this is a factor. 2 times 5 is equal to 10. That is 2 is a factor of 10 and 5 is a factor of 10. So this here looks like a product of something. And that product must have 5 to the power of t inside it. And also must also have 2 power of t. So I must have something like this. 5 to the power of t and 2 to the power of t. Or I decided to change, let me change the variables. Let me use the red marker because I want the video to be like a red pen, blue pen. Okay, so we have 5 to the power of t times 2 to the power of t. That will give us 10 power of t. But we also need to have minus 2 to the power of t. And to have minus 2 to the power of t, then here should be minus 1. Here should be minus 1. And we also need minus 5 to the power of t. To have minus 5 to the power of t, we need minus 1 here. And finally, if you see minus 1 times minus 1, that gives us plus 1. If after solving, like after I reach this point, and let us say here was plus 2, and I got minus 1 times minus 1 as plus 1, then all I'll just need to make it equal, I'll just add 1 here. But in this sense, you know what we have done now, they are equal. So you can just write this. So we have 5 to the power of t minus 1 times 2 to the power of t minus 1 is equal to 10 to the power of t minus 2 to the power of t minus 5 to the power of t plus 1. Don't forget, we're not through yet. Divided by, actually, writing this method is very hard, so I'm not going to continue this way. It's divided by t. Okay, let me just read one last time so that this t will not confuse you with tan. Divided by t tan t. Good. Now the next thing I want to do is I'm seeing this here multiplied by something here. This here looks to me like the limit. That is the limit that leads to natural log of 5, and here looks like the limit that leads to natural log of 2. So what I want to do here is to complete this limit. And to complete this limit, we have what we have here is 5 to the power of t minus 1 times 2 to the power of t minus 1. To complete the limit, I need something that will divide t here. Good, we already have t. By the time you divide t, like you have t in the numerator here, you can just put that t in the numerator here. But if I put this inside the numerator here, which t would be here? You know what we do? We add that t. It's all that will put that t. But to balance everything off, since we are dividing by t, we have to balance it off by multiplying by t again. Divided by tan t. I'll go over again and explain what I just did now. We have 5 to the power of t minus 1, but this is not the complete form of a standard limit. To make it a complete form, we have to have 5 to the power of t minus 1 divided by t. So I'm going to write that down. 5 to the power of t minus 1 divided by t. The next thing that we have is 2 to the power of t minus 1. There's no other t in the numerator. We have already used up that t. But what we're going to do is to add that t in the numerator, then balance it out with another t in the numerator. It's basically just multiplying here by t over t, basically. Probably multiplying here by t over t, and t over t is 1. So multiplying by 1, which is, give us the same thing. So we're multiplying here by t and we're multiplying the numerator by t. We're using 1t in the first expression, we're using second t in this next expression, and finally we're left with divided by t here. So we have 5 to the power of t minus 1 divided by t times 2 to the power of t minus 1 divided by t times t divided by tan t. Good and fine. Now, this here is the standard limit. Here to the standard limit as t tends to 0. And let me show basically what that is. That this limit is going to equal, that is, if you have the limit as, let's say, let's use t, as t tends to 0 of a to the power of t minus 1 divided by t. This limit is the natural log of a. You can get this by applying the star rule, or if I want to mostly algebra, no the star rule here. But if I want to use algebra to solve this, then first of all we need to look at what is, that is Euler's number is. Euler's number is defined as the limit as x tends to 0, no, as x tends to infinity of 1 plus n to the power 1 plus 1 over n to the power of n. This is equal to, that is, if you are putting bigger and bigger number in n, 1 plus 1 over n to the power of another very big number, you get e as our Euler's number. Now what I want to apply here is I use x here, that means here of x. Let x equal to 1 over n. Then this will equal to the limit as n tends to, if x tends to 0 and infinity, then n tends to 0. That's 1 over x, 1 over infinity, which is 0. So n here tends to 0. Of 1 plus 1 over x equals to n, and x equals to 1 over n. And this here should also equal to the limit as n tends to 0 of, the limit as n tends to 0 of 1 plus n to the power of 1 over n must also equal to e. The second thing I want to do is, since we have a to the power of t minus 1, let's apply a u substitution here to make things easier. Let's apply the u substitution. Let's u equal to that a to the power of t minus 1. If u equals a to the power of t minus 1, this implies that u plus 1 is equal to a to the power of t. This means that the natural log of u plus 1 should equal to t ln a. Now the reason why it's t ln a, don't forget, if you have natural log of a to the power of t, you can bring down that t to the front of the natural log. So you have t times the natural log of a. But we're not looking for t times the natural log of a, we're looking for t. So divide out by ln a. Divide by ln a. So if u is equal to a to the power of t minus 1, then t will equal to the natural log of u plus 1 divided by the natural log of a. I believe you understand this point. Good and fine. Now, we are looking for this limit. All these are just standards. I just wanted to, sorry, not down here. All these are just standard definitions for the natural log of e. We are going to apply this one. This was just the first one, but we made this substitution to give this second way of representing e. But this one is what we're going to use in solving this. I'm not showing here. So this is not actually the distribution. You already know it. This is not there, so you already know it. Okay. We have a to the power of t minus 1 is equal to what? U. So this limit, this is u divided by, and t here is equal to the natural log of u plus 1. Don't forget that dividing the numerator is just like multiplying the numerator. That is, if you have a divided by b divided by c, this division in numerator is just something as ac over b. So here is u times natural log of a divided by the natural log of u plus 1. Now, what will the limit be in terms of u? If t tends to 0, then a to the power of 0 will tend to 1. And u equal to 1 minus 1, which is 0. So u here is also tending towards 0. So as t is tending towards 0, u is also tending towards, not 6, u is also tending towards 0. Good and fine. Now, what are we going to apply next? This ln a, I know, as I said, this ln a has nothing to do with u. Ln a is a constant. So no matter how much u changes, ln a does not change. No matter how much u changes, a does not change. That the natural log of a will also not change. So I can bring out this friend that we have here. Let's bring him out. So we have the natural log of a times, no need to apply, let me just write times to avoid confusing with x, times the limit of u as u tends to 0 of u divided by the natural log of u plus 1. Good. Now this does not look like this, right? But we need to do one more step. Since we have multiplying in the numerator, as I said, multiplying in the numerator is same as dividing in the denominator. So since we have u here, we can just remove this u here and turn it to 1 over u in the numerator. And what I tell you that last time when I did this, when I brought down this t down here, I told that when you have something in front of the natural log, you can take it to the power inside the natural log. If you have the a to power of t, you can bring down the t. If you have t to a, you can raise t back up. So now that we have 1 over u here, we can now raise that 1 over u back up inside the natural log. So this was the natural log of u plus 1 to the power of 1 over u. Good and fine. Now, because sorry, there's still one here. It was u that was there, but since I brought down the u in the denominator, what will be on top of the 1, not 0, the 1 that was there. You can see that this limit here look awfully alike like this limit here. We have 1 plus n, we have u plus 1. It's just same as 1 plus u. U plus 1 is same as 1 plus u. We have 1 plus n, we have 1 plus u. We have 1 over u, we have 1 over n. So they are similar. Let me just see, they are alike. So since this limit as n tends to 0 is same as the limit as u tends to 0, we can just change all this 1 plus u to the power of 1 over u. And just change that to e. The natural log of e is same as log e base e. Log s base s is equal to 1, so log e base e is not equal to 1. So the natural log of e here is same as 1. So all we're left with is the natural log of a times the limit of 1 as u tends to 0. Since there's no more u inside this limit, all our answer here is just equal to the natural log of a times 1, which is equal to the natural log of a. So the limit of a to the power of t minus 1 divided by t as t tends to 0 is equal to the natural log of a. I've written that down here. So I'm just going to put a blue box around that because we will still use it later on in our solutions. I'll just put that to the blue box around that. So this is like our standard integral, our standard integral, our standard limit. Okay. Just like in some previous video, I believe I showed that the sin x over x as x tends to 0 is equal to 1, and cos x minus 1 over x as x tends to 0 is also equal to 0. I believe I showed that in the other video. So this is just another form of another standard, limit that we have. I just showed the proof behind that. Okay, we're going to apply this here. Over here, we can see that we don't have 8 to the power of t minus 1 over t. What we have here is 5 to the power of t minus 1 over t. And that will equal to what? The natural log of a. And a here is 5. So that is going to equal to the natural log of 5. Times what? We have the same thing, the same scenario here. 2 to the power of t minus 1 divided by t. They look so much alike. So this is just going to be the natural log of 2. So not the natural log of 2. Good. Now this is another standard integral. The same way you have sin x over x as x tends to 0 is equal to 1, and cos x, I've already seen it before, but cos x minus 1 divided by x as x tends to 0 is equal to 0. Let's say we have tan t t over tan t as t tends to 0 is equal to 1. Should I show this? Let's show this. Okay, we have t here divided by this tan t is something as sin t over cos t. So we have sin t here over cos t. What I tell you, when you are dividing the numerator, you something and multiplying the numerator. So this divided by cos t, I'm going to turn into t cos t in the numerator. So we have t times cos t divided by sin t as t tends to 0. Now you cannot just substitute t inside, because if you substitute t inside, you have t we have 0 times cos 0 divided by sin 0. Does not make sense, right? But then if you look closer, you will see that there's t over sin t here. What I tell you, I think that sin 0 divided by 0 is equal to 1. So t divided by sin t as t tends to 0 also equal to 1. So all this here will just be 1. 1 times cos t. And what is cos t as t tends to 0? That will be cos 0. Cos 0 is equal to 1. So you have 1 times 1, which is just equal to 1. This is all equal to 1. So let me just write that down here as another important limit. Not really important because this is the first time I'm actually saying it. And I just got this proof copied right now because I actually did not know how to prove this, but I just know that this is standard limit t divided by tan t as t tends to 0 is equal to 1. But I just didn't know how I'm going to explain the proof to you. But yeah, just come out of the blue, man. You know, as I said, maths is always true. Maths will never lie to you. Unlike English, yes, that is shade to English. Unlike English, maths will never lie to you. So no matter how you, I don't know how to explain, but no matter which guesses you make in maths, as long as you're making the right guesses, you get correct answers. Please let me confirm if these things still recording. Okay, it's still recording. So I'll continue. So this okay, let me finish this limit. Let me write in the standard form, which is the numerator is going to have the trig function. So we have tan t divided by t. Let me change this lettering. Tan t divided by t. Let me put it. This is equal to 1. Let's put a blue box around that. What is next? Multiplication. This times this is just going to be basically this is just our answer. Finally, 5 times 2. There's no other simplification I can do about this. 5 times 2 is our final answer. You cannot bring this thing together. No, we cannot have 10. This is not not correct. So our final answer just 5 times 2. Good and fine. So this is our limit. The limit of this. I made a very big mistake at the beginning. This is supposed to be limit as t tends to 0. Yeah, this was the limit of this as t tends to 0. Not just this. This was the limit as t tends to 0. Okay. The limit is equal to 5 times 2. To clean it off. The second thing I want to do now is to apply L'Hospital rule to this. That is show that L'Hospital rule will okay. But the first thing before you apply L'Hospital rule, you have to make sure it's in an indeterminate form. If I plug in t equals to 0, I'm going to have 10. No, I'm going to have 1. 1 minus 1 minus 1 plus 1. 1 minus 1 is 0. Minus 1 plus 1 is 0. So all here in the numerator is going to be 0. If I put t equals to 0 here, I'm going to have 0 times tan 0, which is just 0 times 0, which is 0. So I have 0 divided by 0. So it's an indeterminate form. So L'Hospital rule will work here. Let's apply L'Hospital rule quickly. So first of all, let's differentiate this numerator. If you differentiate the numerator, you're going to have 10 to the power of t ln. I don't know how this to write. I don't know how to write this thing. Okay. This will confuse me. 10 power of 10 red marker. 10 power of t ln 10. Okay. Minus 2 to the power of t ln 2. There's no space, so I'm going to write it down here again. Minus 5 to the power of t ln 5 and plus 0, because if you differentiate 1, you just get 0. All divided by, if you keep this one is Taylor's rule. So what you do, you keep t constant, differentiate tan t. If you differentiate tan t, you're going to have sec square t. Okay, plus keep tan t constant. Keep tan t constant. Then differentiate t with respect to t. You are going to have 1. So all you have here is tan t 10 to the power of t ln 10 minus 2 to the power of t ln 2 minus 5 to the power of t ln 5, all divided by t sec square t plus tan t. Good and fine. So now let's apply our substitution and see if we still have an intermediate form or we have a specific number. If you apply t equals to 0 here, what you are going to be left with here is 10 to the power of 0, which is 1, times ln 10. So I'm going to write ln 10 here. Minus 2 to the power of 0 here will be 1 times ln 2, which is ln 2. Minus 5 to the power of 0 here is 1 times ln 5, which is just ln 5. Good and fine. All divided by, if you plug in t equals to 0 here, you are going to have, yes, this is also going to be an intermediate form, because this is ln 10 minus ln 2 minus ln 5. This here will give you 0, because minus ln 5 minus ln 2 minus ln 5 will give you minus ln 10. So you have ln 10 here minus ln 10, that will give you 0. And in the numerator, I'm looking at it, I'm seeing t equals to 0. So here will just be 0 plus tan t will be 0, so that's 0. So I'm seeing another, 0 over 0. So all I'm going to have here is 0 divided by 0. So what we're going to do, we're going to differentiate a second time. I'm going to differentiate a second time. This is us differentiating the first time. So I'm going to leave this here and differentiate the second time. And when I differentiate the second time, ln 10 will be a constant. Ln 5 will be a constant. Loan 2 would also be a constant. You understand? Okay, that's all the constants. Loan 10, loan 2, and loan 5 will be constant because they don't have t inside them. So let's differentiate the second time. If I differentiate the second time, well, first of all, we're going to differentiate 10 to power t. 10 to power t will give us 10. 10 to power t will give us 10 to the power of t loan 10. Don't forget there's another loan 10 here. So this will become loan square 10. Minus, if you differentiate 2 to power of t, you still have 2 to power of t loan 2 again. Don't forget there's a loan 2 that was already here. So that will be loan square 2. If you differentiate 5 to the power of t loan 5, you have minus 5 to the power of t loan 5. Don't forget there's still loan 5 here. So this will be loan square 5. All divided by, differentiate this. What you're going to do is keep t constant, then differentiate sec square t plus keep sec square t constant, then differentiate t. Then if you differentiate t, you're going to get 1. So that will just be sec square t plus differentiate tan t. What you're going to be left with is sec square t. Now what we're going to do now is to substitute in our value for t. We have differentiated the second time. Let's substitute in our value for t and see if we still get an indeterminate form. If you substitute t inside here, you have t to the power of 0, which is 1. So you are going to be left with loan square 10 minus loan square 2 minus loan square 5 divided by, if you put in t equals 0 here, all this will equal to 0. If you put t equals 0 here, here is equal to 1 over cos square 0. So that will just be 1 over 1. So that is 1 plus 1. So this all in all, this just plus 2. Good. Now what do we have here? We have loan square 10 minus loan square 2 minus loan square 5 divided by 2. This loan square 10 minus loan square 2. Let's handle this first of all. We have loan square 10 minus loan square 2. Okay, let me do that here. We have loan square 10 minus loan square 2. This will equal to loan 10 minus loan 2 times loan 10 plus loan 2. Don't forget minus loan square 5 divided by 2. So we have difference of two squares here. We have loan 10 minus loan 2 times loan 10 plus loan 2 minus loan square 5. Loan 10 minus loan 2 is same thing as loan 5. So all this here is all equal to loan 5. Okay? Loan 10 plus loan 2 is equal to loan 20. So all this here is equal to loan 20. The second thing I want to do now is to factorize out loan 5. We have loan 5 here, this will be minus. We have loan 5 here, we have loan 5 here. So let's factor out loan 5. Factor out loan 5, I'm going to have loan 5 times loan 20 minus loan 5. Don't forget, divided by 2. Loan 20 minus loan 5, same as loan 4. And loan 4 divided by 2 is same as half loan 4. And half loan 4 is same as loan 4 to the power of half. And 4 to the power of half is same as 2. So all we're left to get is just loan 5 times loan 2. So this is also equal to loan 5 times loan 2. Let me write that in red marker just in case the camera I'm not capturing blue marker. So that my work will not be wasted. Loan 5 times loan 2. You can see that we had the same answer from the previous one, even if we use plus rule or we use algebra. No matter which method you choose to use, you would always get the same answer. I believe you understand your rule. We differentiated the first time, but it still gave us an indeterminate form. Okay, it gave us 0 divided by 0. So I told you differentiate the second time, and we could apply some things. So we could cancel out some things. So now we got loan 5 times loan 2. The same answer as the previous one. So now let's take this question. We've used two methods now for this question. Let's move on to the next question. Okay. See, I wanted to keep that thing. I wanted to keep those standard limits. But I've already cleaned it. So I'm just finish cleaning this. I wanted to keep those standard limits. Sorry. Okay, now let's move on to the second question. The second question asks us to find the limit as x tends to 0. Let me use red pen for this. X as x tends to 0 of p to the power of x squared, okay, minus cos x divided by x squared. So we have the limit as s tends to 0 of e to the power of x squared minus cos x divided by x squared. Now I'm going to also apply three methods to solve this. The first method I want to apply now is Taylor series. I'm not going to go on proving the Taylor series. I already have it written down here. We have this is the first method. Let me put hashtag 1. The first method. We have the Taylor series for each power of u. Let's say each power of u. So we have each power of u. This is equal to 1 plus u plus u squared over 2 factorial plus dot dot dot. We have a standard Taylor series for cos x. So cos x is equal to 1 minus x squared divided by 2 factorial plus h to the power of 4 divided by 4 factorial minus dot dot dot. We go and find what else do we need. So those are the two functions that are there. Each power of a number, each power of u and cos x. So now let's substitute u equals x squared, because here we're giving each power of x squared and not each power of u. So let's substitute u equals x squared. If you substitute x squared for u, then e to the power of x squared will equal, let me use red for x in this thing, so you know where x is, where x is. Okay. So we have e to the power of x squared will equal to 1 plus x squared plus x squared to the power of 2 divided by 2 factorial plus dot dot dot. Good. And cos x already given as x. So we have these two expressions. And we are giving each power of x squared minus cos x. So we are going to have this term here minus all the terms here. Good. So this limit, let's call this limit I or L. Let's call this limit L. I know for integral, I say let's call integrals I. So for this limit, let's call the integrals. Let's call the limit here, not integral. Let's call the limit here L. So L is equal to each power of x squared minus this will be same thing as 1 plus x squared plus x to the power of 4 over 2 factorial plus dot 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 minus cos x is going to be 1 minus x squared over 2 factorial plus x to the power of 4 over 4 factorial minus dot dot dot, all divided by what? X squared. Good. Now let's remove the things that we need. Let's remove all the terms that have x squared basically, because x squared is what's the numerator here. I want to make sure that the numerator here is not going to have 0. So let's remove all the things that we need, which is basically the ones that are less than or equal to x squared. Okay. So this our L is going to equal to, let's remove 1 and 1. There's 1 here, there's 1 here. There's minus, so that 1 minus 1 is 0. X squared minus x squared over 2, which is just going to be x squared over 2. We have x squared minus x squared over 2, we have x squared over 2 plus x power of 4 over 2 plus x power of 4 over 4 factorial. That was just basically x power of 4. Or let us use this term, O times x power of 4, which means that all the terms that are greater than x power of 4 over 2 factorial here would all have terms that we have x that have a higher degree than 4. That's all the x terms that after x power of 4 over 2 factorial would have higher order, higher degree than 4. And the same thing happens here. All the terms after x power of 4 over 4 factorial would have higher degrees than 4. So let us use O times x power of 4 here. So we have 0 plus x squared over 2 plus O x power of 4. So this 0 you can cancel it out. All divided by what? X squared. This x squared here can cancel out this x squared that's up here. So we have x squared here, cancel out this x squared that's up here. and we are left with 3 over 2 plus O x power 4. Okay. This is 1 minus 1. This is x squared minus x squared over 2. So that will be x squared plus x squared over 2. That will be 3 over 2 x squared. So this will be 3 over 2 x squared. 3 over 2 x squared. This is all divided by x squared. So the x squared will cancel out. This will be 3 over 2 plus O x power 4. So if you substitute that x equals to 0, everything here will have a higher power than divided by 2. So everything here will equal 0 because they will all have an x term inside them. Everything will have an x term inside them. So all this can cancel out. And we're left just 3 over 2. So our limit will equal to 1.5. So this for hashtag 1, our limit L equals to 1.5. Let's go on for the next. Let's go on to the next method. Or let me just explain that O basically. When I was showing the proof for sine x divided by x, I told you that sine x is equal to x plus x squared, no, not x squared, x cubed over something. I told you x cubed over, I can't remember the Taylor series for sine x, but x plus x cubed over something. So by the time you divide by x, you have sine x over x is going to equal to 1 plus x squared over 2 of x squared over the numerator that was here plus x power 4 over the numerator of in that place. So if you put in x equals 0, everything here that is greater than 1 all have a factor of 0. So all will be cancelled out. That is something that happened here. Everything that is greater than x squared here will all be cancelled out because we still have a factor of x. So they'll all be cancelled. That is just as O bracket x power 4. So this limit here is equal to 1.5. The second method I want to apply now is algebra. This one was using Taylor series. Second one now. So for this one, we have e power of x squared minus cos x divided by x squared. There's another standard integral which is e to the power of x squared minus 1 divided by x squared is equal to 1. And how do we show this? We can show this actually from using that first law. I thought I wanted to do those standard integrals that we just showed now. But I told you people that if you have a to the power of t minus 1 divided by t, I don't know if you can still remember this, just a minute ago. A to the power of t minus 1 divided by t, as t tends to 0, this limit is equal to ln a. So in this case now, we have e to the power of x squared minus 1 divided by x squared. If we say let t equal to x squared, then we have e to the power of t minus 1 divided by t is equal to something. This here is standard integral. So this what is equal to the natural log of this base here, and this base is to that natural log. So all this here is equal to 1. So e to the power of x squared minus 1 divided by x squared, the limit as x tends to 0 is equal to 1. So good and fine. Let's write this down here. The limit I want to show right now is the second limit I want to show right now is 1 minus x squared. 1 1 1. Here with minus 1 plus 1. Okay, the 1 minus x, no, 1 minus cos x divided by x squared. I know some people will be like as x tends to 0. I know some people will be like, it's not supposed to be 1 minus x, 1 minus cos x divided by x. Why is it x squared? Well, this is the way it came. So to solve this, we have to multiply this here by 1 plus cos x divided by 1 plus cos x. Now multiplying this by this, because this is the conjugate, 1 plus cos x is the conjugate of 1 minus conjugate. Yeah, the conjugate is 1 plus cos x is going to equal to the conjugate of 1 minus cos x. And don't forget, when you are dealing with all these things, when you are rationalizing, you multiply, you just change the sign. If you have minus a, you can just change to plus. If you have plus, you change to minus, then multiply both the numerator and numerator. So I'm multiplying numerator by 1 plus cos x, and I'm multiplying numerator by 1 plus cos x. So 1 minus cos x times 1 plus cos x will be 1 minus cos square x. And I know some people are already shouting, is that not sine x? They are correct. This is all equal to sine square x. Divided by, we have x squared in the numerator, and we have 1 plus cos x, which is being multiplied with it. Good and fine. I forgot to snap. I just remember. I forgot to snap out that. Okay. So now we have sine square x divided by x squared times 1 plus cos x. This sin square x divided by x squared, same thing as sin x divided by x all squared times 1 over 1 plus cos x. Good. Now what do you know about sin x over x? As x tends to 0, sin x over x is going to equal to 1. So sin x over x here is going to equal to 1. And 1 squared is equal to what? 1. So we can cancel all this out. So all we're left is just 1 divided by 1 plus cos x. As x tends to 0, cos x will tend to 1, cos 0 is equal to 1. And 1 plus 1 is equal to 2. So all we're left is just going to be 1 over 2. So this limit, let me write it down here. The standard limit as x tends to 0 of 1 minus cos x divided by x squared is going to equal to, what did you just solve for minus cos? Go equal to 1 over 2, yeah. Go equal to 1 over 2. Good. So I said this is different from 0. The other one, 1 minus cos x divided by x will give you 0. But in this case, you have 1 minus cos x divided by x squared. This should equal to we have. Good. So now that we know these two things, we have them at the back of our pocket. Let's now solve this limit. So this limit now we have e to the power of x squared minus cos x divided by x squared. We want to apply these two limits, but there is no minus 1 here and there is no plus 1. What can we do? Add them. If you have minus 1 plus 1, it's just 0. So when you are adding 0 and you're minusing 0, you are doing nothing to the expression. Except actually you're making it simpler, but like you are not changing it, it's still going to be the same expression. Minus cos x. So now we have e to the power of x squared minus 1 plus 1 minus cos x. This minus 1 plus 1 infinity, they'll cancel each other, so just give back the same thing. But to make it easier for us to solve, we put it like this. So now let's carry out the first two terms and separate out the last two terms. Now we left e to the power of x squared minus 1 divided by x squared plus 1 minus cos x divided by x squared. We've already solved these two limits now. This one gave us 1, and this second one gave us a half. So all we're left is just 1 plus a half, which is equal to 3 over 2, which is also equal to 1.5. The same as what we got the last time. L for the second case is equal to 1.5. So this is the second way to solve it using algebra. Now the third way I want to show it is to solve it using L'Hospital rule. After I like L'Hospital rule because though I'm not going to, actually I'm going to use it in test reviews. I'm going to explain L'Hospital rule again in test review because I feel like it's a very, very good shortcut for students to have at the back of their head whenever they're solving these limit questions. And don't waste their time, trying to see should they rationalize, should they factorize, should just apply the L'Hospital rule and rest of it. Though there are times that applying L'Hospital rule is actually harder than solving the question. Let's apply L'Hospital rule here. L'Hospital rule says that we should differentiate numerator divided by derivative of numerator. So let's differentiate numerator. If I'm differentiating e to the power of x squared minus cos x, so the same thing as differentiating e to the power of x squared minus differentiating cos x. So by differentiating e to the power of x squared, first of all, we have differentiation what's at the top. We have 2x times, or let me just explain it for those people that also don't know the derivative. So now let's differentiate e to the power of x squared minus cos x with respect to x. This derivative is equal to the derivative of e to the power of x squared with respect to x minus the derivative of cos x with respect to x. This here now is a chain rule. So if we say let u equals x squared, then du dx will equal to 2x. Good. If you put in u equals x squared here, then we are going to be left with the derivative of e to the power of u divided by dx will equal to du over dx times the e to the power of u divided by du. So the e to the power of u, that is e to the power of u with respect to u, is also going to give you e to the power of u. Of course, nothing changes e to the power of u. If you derive it, you integrate it, you get e to the power of u. Du dx, we already solved that as 2x. So if you differentiate e to the power of x squared, all you left is 2x times e to the power of x squared. So I'm just going to write down 2x times e to the power of x squared minus, if we differentiate cos x with respect to x, you are going to get minus sin x. So minus and minus have plus sin x here. Okay, don't forget about also differentiating the numerator. If you differentiate x squared, you're just going to be left 2x. So all you're left now is 2x times e power of x squared plus sin x divided by 2x. If I now apply that limit, that is putting x equals to 0, you will notice that here you are going to divide by 0. So I'm not going to apply the limit now. What I want to do now is a little bit of algebra, which is like moving this 2x with the first term and moving this 2x with the second term. That is, we have a plus b divided by c, same as a divided by c plus b divided by c. So we have 2x e to the power of x squared divided by 2x plus sin x divided by 2x as x tends to 0. This 2x will cancel this 2x here, so I just have e to the power of x squared plus sin x divided by 2x. E to the power of x squared, as x tends to 0, x squared tends to 0. As x squared tends to 0, e to the power of x squared will tend to 1, because e to the power of 0 is equal to 1. So this here just goes equal to 1. Okay? Sin x over x, as x tends to 0, is already a standard integral. I said that is equal to 1. So half times sin x over x equal to half times 1. So this will just be 1 plus a half. And 1 plus a half is equal to 1.5. The same as the last other two solutions. 1.5. Good and fine. The final question says, now this final question actually, we'll just see how we do it, how we can solve it. Okay, we have the limit as something x tends to infinity, okay, of x plus sine x divided by x plus cos x. So we have the limit as x tends to infinity of x plus sine x divided by x plus cos x. Good. This question actually stunned me. I was like, wow, so they can ask me a question, which is pretty amazing. But how do we solve this type of question? I'm going to actually solve this using the algebra. And to use algebra to solve this, we first of all have to factor out x from this and factor out x from this. So if you factor out x from the numerator, you're going to be left with x. Let me use left hand. I'm going to be left with x times. If you divide x with x, you'll be left with 1. That will be x times 1, which is x, plus. If you divide sin x with x, you're going to be left with sin x over x. Okay? Now for the numerator, factor out x, you'll be left with x, bracket open, 1 plus cos x over x, bracket close. So now, what do we do next? First of all, this x here can cancel out, but let's do that for now. Let's look at this sin x here and let's look at this cos x here. Sin x oscillates between 1 and minus 1. So sin x over x, as x tends to infinity, sin x will still be oscillating between 1 and minus 1, even as x tends to infinity. Sin x will still be between minus 1 and 1. It will never be greater than minus 1, it will never be greater than it's never less than minus 1, it will never be greater than 1. So as x tends to positive infinity, sin x over x tends to 0. Because this sin x over x will be so small, just between 1 and minus 1. It will be so small compared to the infinity. I believe this should be a theorem. There's no theorem under this. I believe I want to find this out. I want to call this my theorem. But apart from it's already a theorem. Squeeze theorem. Sin x over x as x tends to infinity. Sin x over x as x tends to infinity. No, as x tends to infinity, not 0. 0. As x tends to 0 is 1, but as x tends to infinity, it's not going to be 0. It's not going to be 0. Sin x over x. No, that sin x will be between minus 1 and 1. So it's not, it can never be compared to infinity, that will be like numerator. So just be like 1 divided by infinity. There's a note for sign. The limit is from 1 to 1. The limit from negative 1 to 1. Yeah, so that x, so I cannot have x tends to infinity for sin x. That's a domain. Yeah, the domain, that is the y value, that is the value of sin x itself. X can. No. Okay. Domain is x value. Domain is x value. Domain, no, the domain, can the domain of x of sin x be like all the real numbers? Then the y value is now the sin x.
Okay, yes.
So sin x over x. Fun. So we have sin x over x. This sin x over x here will just be 0 as x tends to infinity. And this cos x over x, the same thing applies to cos x over x. Since cos x oscillates just between -1 and 1. -1 and +1. Since oscillates between -1 and +1, you have a very small number divided by the biggest number you can think of. That is just going to be 1 divided by infinity. You know that this is also going to be 0. So this here too also gets 0. Let's see. So if we substitute all things that we know, we are going to be left with x here times 1 plus 0 divided by x times 1 plus 0. The numerator is same as the numerator. So you can just cancel out everything that you have. X here cancels x here. 1 plus whatever cancel out 1 plus 0. All you have is just 1 here. So the limit of x plus sin x divided by x plus cos x as x tends to infinity is going to give us 1. What if x tends to negative infinity? I'm not allowed to think about that. But if x tends to negative infinity, what would the limit tend to? What would the limit tend to? Yeah, I will just give you a little bit hint. It's the number starts with 1 and end with 0.00000. The answer is still 1. As x tends to positive infinity or negative infinity, we are going to have 1. Because the same thing applies to sin x. Even though sin of negative infinity, it's still oscillate between plus and -1 divided by a very big number, which would be like a very big negative number, which just be minus 0. So this kind of thing happens. So that's just 0. Plus the same thing happens here. You have -0, but then this is 0. The minus not affect anything. So you have x over x, which is 1. So when x tends to positive infinity or negative infinity, you still have positive 1. So yeah, I think that's basically all of it. Nothing much with the question snapped again. Okay, what else can I say about this question? I'm still looking, because what I did here was I still applied the theorem here. I not fully did algebra. I still applied that hypothetical guess of sin x over x as tends to infinity. Okay, but I'm still looking if there's a way of doing this purely by algebra, maybe by multiplying here by. So I believe this is the simplest way to solve this question. But if you feel you have a simpler way of solving this, I feel this is simple, but if you can solve this using purely only algebra, you can solve this using purely only algebra, then please you can comment a solution for me. Let me also learn. But so far, I'm not saying you to solve this using only algebra. But yeah, that brings us to the end of this. That brings us to the end of this video. I hope to see you in the next one. Also, I'll do a little bit of advertisement at this point in time. I've not tried it, but I get permission for this. But there's a book that I'm making. I'm getting permission to sell the book. If the book is permitted, then the book will be going for 500 naira. Yeah. So you can come and buy the book, purchase the book. Every week, a new version of the book coming out because every week we'll be having classes. So questions from practice questions from the lecture added to it. The way I'm seeing the mark question guide or the past questions, I'll be adding questions from here. So the book will be getting bigger and bigger by the week. So you can come every week to be renewing or to be getting the latest edition. But yeah, it's still on sit with the management to see the ask for permit it. So yeah, if the permission is granted, you can do that. Another advertisement is 1 year calculus. 1 year calculus is still holding. I'm just creating a website for it. So that's why I've stopped posting videos on it. I'm going to start creating solution videos for it from now on. So 1 year calculus is still holding. Well, probably less than like I think we'll be in 15 by now. So you can still join the challenge at IgweMatics.blogspot.com. You can join the challenge, answer the questions there every week. You're coming for just one calculus question for the week. Solve it for the week, submit a solution, and get marked. So yeah, that's basically all the advertisements at this point in time. Thank you for watching this video. I'm Bernard.